Welcome. In this session, we'll be considering how we can visualize and analyze our molecular docking results. We've carried out molecular docking using PyRx and we've gotten our molecular docking scores. Now, the next thing is to analyze those results using PyRx and then visualize them using Discovery Studio. Now, the software that you require for this process includes PyRx. PyRx was the software we used for docking. Remember, it contains Autodock and Autodock Vina, and we used Autodock Vina. We also use it for analyzing our docking scores, which refers to our binding energy. Now, we will also be using Babel to convert PDB-QT files to PDB files. If you remember, when we wanted to carry out docking, the files were converted to PDB-QT, and then for visualization, we'll have to convert them back to PDB files. And finally, we'll be using Discovery Studio to visualize the interactions responsible for the docking scores or binding affinity that we got. Now, the interactions are interactions between the ligand and the target protein, which is the receptor you're working with. Now, in analyzing your results, it's important you take note of the binding energy. For some algorithms, they would have different scoring functions or different forms of this binding energy, but for Autodoc Vina, we use the word binding energy. And the more negative the binding energy, the more stronger the interaction. Let me show you what I mean. Now, this is the results we got from our docking, and then if you look at our results, we have ANP, that's the crystallized ligand, minus 8.2. We had other compounds from natural sources from plants giving us minus 7.5, minus 8.4, minus 8.8. So it means that if we consider the compounds we worked with now, looking at then we considered about that should be 8, 1, 2, 3, 4, 5, 6, 7, 8. We will see that the best was this because it had the most negative binding energy. And I've told you the more negative the binding energy, the better the interaction. I'll be more detailed about this when we uh, consider this data in the Excel file. Now, another important thing you need to also be aware of is the RMSD value. RMSD refers to root mean square distance, and that's actually a measure of the deviation of the poses you have from the reference pose. And according to several studies, when you have RMSD values that are less than 2.0 Armstrong units, it means that it's good. Between 2.0 and 3, it's acceptable, but once it's higher than 3.0, it means that pose is actually totally um, different from the reference pose and references, and then eventually that result is often unreliable. Now, so I'll take you back to the result and then you can look at it. You can see some of the RMSD values for the upper bound, you have them here, and then the lower bound, you have them here. Now, once the value is higher than 3, it's always an issue, but if it's less than 3, around 2, or even less than 2, then it's fine. Now, beyond this, let's go to our Excel file. So if you remember, I saved the docking result as a CSV file. And then that's what we had here as a CSV file. And then I've renamed it. So we have berberine, and then this is the binding affinity. We have the root mean square deviation, this upper bound, and this is the lower bound. And like I've told us, once the values are above 3, then it's a source of concern. Look at this. This is quite good because both the RMSD value for the upper bound and the lower bound are actually less than 2. Now, we'll be taking the docking scores we've gotten. So how do we um, work on these results? We have a lot of results, but we are not going to be using everything. Now, and all these results also represent different poses. So if you observe this, we have about 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 poses for each compound, 9 poses for each compound. And the one with the best RMSD value for this is this, and then it's minus 7.7. But a lot of times we go with the most negative value, and that's what we will do. But if you want a more detailed explanation, because there are times you will not just use the most negative, you are also considering the pose. There are times you do that. Now, so let me work on this result. So let's go to um, insert a pivot chart. Okay, a pivot chart and a pivot table. Oh, sorry, we've not selected this. So let's insert. Okay, so good. Now I often want to work with the ligand and then the binding affinity. Now, once you click on this, it will bring it like this. But what you do is go here and then click on this, and then we want the minimum value. Now you can see that. So you see that the co-crystallized ligand is minus 8.2, while routine is minus 8.8. Now metformin, a drug, is minus 4.4, while rosiglitazone, another drug, is minus 6.8. So this tells us that some of our compounds, such as rutin and berberine, performed better than the co-crystallized ligand and even the standard drugs. It meant that they had better interactions with the target protein, and they are likely to be potential modulators in this case of that target protein we're working with. Don't forget, we are working with the target protein, and then you can visualize this using um, different kind of visualizations, but that's not what we will be looking at today. But this helps you to see, this table helps you to see it clearly, Now, the next thing we intend to do is to carry out a visualization. And to do that, we'll be using Discovery Studio. So go back to Discovery Studio. Now I will open a new molecule window, and then I will import the original protein we worked with. So if you remember, that one, not the one that lacked okay, good. So we have this. Now the next thing I would like to import is the poses of the compound I docked. And how do we get that? And please, it's important to know how we do this. So go to PC, click on, look for users, go to user, then go to .mgl tools. MGL tools. And then click on PyRx, look for macromolecule, and look for what you worked on. 1 IR3 without water and ligand. Now, if you observe, please look at this. The type of files here are actually PDBQT files. And then if you try to import them in Discovery Studio 2024, the structures, you will not even get anything. It will not give you any structure you can work with, because the whole structures will have been broken down. So what we do is to look for another file that is able to couple all these structures together and then give us correct structure we are looking for. So we use Babel. Let me explain what I mean so that you understand what I'm talking about. Now, let's try to see if we can import this. And then you'll see the challenge we are facing. So go to File, then Insert, then we will navigate to, remember, users, user.mgl tools, PyRx, macromolecule. Okay, this is it. Now, can you see that? It tells us that it does not support PDBQT, so you're not going to get anything. And then if you try to force it, the structures will be totally broken and it will not make any sense. So what we do is to look for a software that converts PDBQT into PDB, and the software we'll be using is Babel. So let's open Babel. Now, so you must have installed Babel. I will give you a link to all of these software so you can install them, and then you practice while we are also doing it here. So open Babel. Good. Now, so what do? You navigate to that place. So this is it. So now the first one is 2353. So you open 2353 and then you come here. Now select PDBQT here. That's the input format. You're converting it to PDB. So click on this. Now I often always want to create a new folder, and the folder for this will be, so we'll call it PDB files. So remember, this is 2353. We will get the name of that compound. This is the PubChem ID 2353. So let's save it, and then what we do is we simply click on convert. Good. Also, we are done with that, and then you can go to the next one, 4091, open, and then you have 4091, and then you also convert. Now 7799, and then you convert. No, that is 969516, 969516, and then convert 5 to 80343, 5 to 80343. Then you also convert. We are changing it from PDBQT to PDB. Then we also have 5 to 80805. 52805. So we convert, we're almost done. This 5458190. So 5458190. We're converting it to this. So, and lastly, we have our ANP, that's the co-crystallized ligand. ANP. So convert. Oh, this is good. So you've converted everything. So you go here, and then what you can do is you can import. So now we are not looking for this. We navigate, user, MG tools, PyRx, macromolecule, and then you can see that. So let's start with the 2353. Let's just see it. You can see that. So with 2353, to see the interaction, you can click on one of them and then click on define ligand. Wow. Now once you click on it, you will see this, and then we can, if we want to see 2D structure of the interaction, then we can click on this. Now let's look at the ligand interaction. You can see some of the ligand interactions, and I know there are interactions you will not want to see, all these ones with red, so we'll work on it. Well, let me show you a 2D diagram to help you. So wow, you can see the interactions, but this does not look good, and I will tell you why. So what we'll do is let's remove the whole water molecules to begin with, and then ANP is also present there, so we don't want ANP there. We don't want this. We don't want this. We don't want this. Now so this shows us 2353. Let's see, 2353 is berberine, and then it interacts with different amino acids. Now I think we can, so that we can see it better. Now so their interactions with glycine and many others. Let's see if we can make it. Okay, now let's work on it a bit. Apply, so you can see this structure. Now another thing we can do is the interaction. So let's see if we can reduce the size of the name. 1.2, so that, oh, it's not helping, so it's not clearer. So but this shows you the interaction between your compound and the different amino acids you are working with. Let's see this. Let's see if it will. Wow. Okay, then we don't want water there. So look at the different interactions. Now you can see that there is a hydrogen bond interaction, Now we often take the first one. We often take the first one, and then there's the interaction we often report because we expect that it's going to be the best interaction. Now you can see that interaction here. Now whatever you have here is what you have here. Okay, so let's reduce this so you can see this. Now another thing you can do with this is you can also allow it to provide information on the types, sorry, on the sizes, on the distance. So you see, these are information on the distance between this docked compound and then this amino acid. And we can even show the kind of interaction, and then we can even choose to put the name. So look at this. So once you click on it, it shows. So that means this is lysine, serine. You can see that serine 1006. That's it. And then the distance is 3.08, and you know it's a conventional hydrogen bond. And these are the interactions responsible for the results you get. So okay, let's click on this background, and we want our background to be white. So you can see that. Can you see that? So the background is white, which is what you often see in publications. Now let's change this label, and then we want, first of all, let's remove these labels, and then we can change the color. Then let's change the color to maybe black or brown. Let's see this. Then we apply. Okay, you can see that. Now we can change this to be Arial. Okay. Okay, so you can see that. So this shows us the interaction. Look at this between this compound and then the different amino acids that are present within the receptor, which is your target protein. And remember, all we did was we simply clicked on this, and then you click on the file ligand. You've already defined your receptor. Now, if you want to visualize this, just click on this, and then we can make this look better. Good, and you can easily save this. Now, once you've visualized, the next thing you intend to do a lot of times is to export what you have. Now, how do you do that? You simply go here and then click on this, then go to File, go to Save As, and you can save it as a graphic file or an image file. So let's say an image file, and then you can save it. You can see that. So you can change the width as much as you want and then save it. Let's say we want 800. So and then we can, okay, and then it will save where we saved it. So it's important you know that you can carry out visualization. Now this means that these interactions are responsible for the docking scores you obtained. For instance, like for 2353, which is berberine, the interactions we found here, let's click this to give you something better. Now to remove something like this, I think you can go to none, go to unsatisfied bond, and then click on this, and then it removes this. And then you can just simply go, let me show you how to save this once more. Click on this and then go to File, go to save as, and you can save it as an image file. Now let's go to downloads and save it here. So let's save it as an image file. Remember, that's for berberine. So berberine 1. So let's save it there. Now let's change this to 800. Now let's navigate to that, and you can see it there. Wow, you can see it is here. So you can click on it to open it. Let's go back here. Now you can also even choose to add the receptor so that it looks. Now let's remove water. Now so that you can see it within the cavity. Okay, so you can see this. You can see that. And then I know some of us have seen things like this. So in case you want to save something like this, it's not difficult. So let me bring. So it's not difficult to save something like this. Choose. Aha! It looks clear, and then you can just simply go click on this. You can then go and then file, and then you can click on file, and then you can save as, and then save as an image file. So let's save it as image berberine on 1 or II. So let's save it as an image file. So let's say this is 800. So let's go back here. We'll find it there. You can see that. Look at how it looks. So you can see that. Thank you for listening. If you have any question, please always get across to me. Thank you.